We'll start a new section, a section on Bayesian updating. We will continue using Bayesian rule now, but instead of using it in the context of decision making and updating the information of the decision maker, we will apply it to learn from data. Idea is the same, and the rule doesn't change. So we want to update the probability over A given some evidence B, and it's just a ratio of the joint probability over A and B divided by the total probability over the evidence B, and the terminology stays the same. So the updated probability we call posterior. This one we call likelihood. So likelihood tells us the probability of evidence given the A, given the parameter of the model, and this is the prior information about A, and this is total probability over evidence B. And the total probability, of course, we know how to calculate. You just have to marginalize A. You take the joint over A and B and marginalize A from this joint to calculate the total probability. Okay, so that's how we update the Bayesian updating. And a lot of the new artificial intelligence based systems rely on the Bayes rule. So if you go back maybe 20-25 years, so the old AI systems, they also were called expert systems. They were basically relying on a Boolean logic. Meaning that the system was implemented as a large number of logical statements, something like if user presses some button, then show information about something. So it was hard-coded rules, and human and machine would interact using those hard-coded rules. So they didn't go anywhere. A lot of the modern computer programming is still Boolean logic. But in a lot of the cases when machine interacts with a human nowadays, instead of using this Boolean logic and this if A then B type of statements, the new AI relies on the Bayes rule. So instead of saying if A then B, the new AI will calculate probability over B given A. So two major differences here. So old AI is deterministic, and the new AI is probabilistic. Another difference, and this seems like another big deal, but it's actually quite important. If you have the statement if A then B, then you cannot say anything about. So if you want to invert it, and if you want to say if B then A, then you cannot really do that. Boolean logic does not allow you to invert those statements. There's nothing you can say about if B then A. However, in the probabilistic world, we can invert it and we can calculate probability of A given B if we know probability of B given A. So somebody coded this one and we have the prior for A, we can actually calculate probability of A given B. So we can do this probabilistic inference, and system becomes more flexible, inference becomes easier, and you can do this probabilistic queries, and instead of just finding the right if-then statement, you actually can calculate the conditional probabilities. And if you ever taken a course on Bayesian networks, so Bayesian networks is all about that. You basically encode those conditional probabilities, and each connection in the Bayesian network is a conditional probability, and then you basically provide values for some of the nodes in the Bayesian network, and then you can infer the values for the other using the Bayesian inference. So that's a big deal, So Bayesian nets is example of that. Bayes nets is example of that. and quite a few interactions of human and machine, which we call artificial intelligence type of interaction, happen this way. Another big difference between the new AI and all AI had to be human coded or handwritten. So in the old AI days, you have to hand code the rules, hand code the rules, those if-then rules. In the new AI, you actually can learn those conditional probability from data. So you learn from data. So learn from data versus hand-coded rules. So that's difference number two, big difference. And difference number one is that here you cannot invert, and here you can invert. Sorry, it's a little bit scattered, but so you get the idea. All right. So let's look at a quick example. Apple Watch. So Apple released a new watch in Series 4 had this ECG sensor, which can detect arterial fibrillation, and engineers were quite proud of this sensor. The sensor was 98% had true positive rate and 99% true negative rate, meaning that if a person has arterial fibrillation, then test will be positive in 98% of the cases, and for people without arterial fibrillation, test will be negative in 99% of the cases. So quite impressive sensor. And here the notation T stands for positive test and AF stands for person has arterial fibrillation. And of course, we're interested in the inverse. We're interested in probability of having arterial fibrillation given the test was positive. So you have this Apple Watch, and the sensor shows that you do have, or positive, it shows you positive result, indicating or pointing to the fact that you might have arterial fibrillation, and you want to calculate probability of arterial fibrillation given the test. So we're going to apply the Bayes rule here. And on the right-hand side, we know the likelihood, we know probability of test being positive given arterial fibrillation, and we need to multiply by the prior over arterial fibrillation, and Apple engineers don't really have to do those things. There is actually medical studies that calculate those things. You can find it through medical literature search, and they were able to find it. It's 2% of the population has arterial fibrillation. So once you know this number, you can calculate the total probability over the positive test. So you can calculate total probability by summing up and marginalizing the arterial fibrillation variable. And if you plug everything in, you actually get 66%, meaning the probability that arterial fibrillation is present given the test is positive is 67%. And the probability goes down quite significantly from this prior, or from this likelihood of 98%. And if you try to picture what is happening, so let's say we have this big square, which is our total population, and then you have this little square here at the top right, at the top left. So that's the people with arterial fibrillation. Okay. And out of those people, you detect correctly 98%. So from this little square, 98% will be correctly detected. On the other hand, you have this large portion of the population, 98% of the population does not have arterial fibrillation. And out of this 98% of the population, you actually incorrectly say that they have arterial fibrillation in 1% of the cases. So if you imagine this, here's another square that basically represents, so that represents 2% of 98 percent. Oh, the true negatives were 99%, so it's actually 1%. So this is 1% of 98% of population without arterial fibrillation. So 98% of the population does not have arterial fibrillation, and 1% from this 98 will be incorrectly detected by the sensor as people with arterial fibrillation. And actually, if you look at the sizes, what you will see that Arterial fibrillation was correctly predicted in 1960 cases, in 1960, and was incorrectly predicted. So the size of this square um, is 2,000. And out of these 2,000, 40 people were missed, and most of them, 1960, were correctly identified. And the size of this square is 980. Okay, so if you take the ratio of those two squares, you actually get 67%. So in 67%, the test will correctly predict arterial fibrillation. And that has a few implications. Now you actually have to think very hard whether you want to have a sensor like that, or if you want to test people, because what happens is um, a person gets a positive test and then starts really worrying about this, and only in 67% he should be worried or she should be worried, and in the rest 33% person should still really do nothing. So you have this 33% of the people who use Apple Watch and get the positive test, they actually start worrying for nothing. But on the other hand, you actually capture arterial fibrillation. So there is a trade-off. And there's a lot of debate usually in the screening policy for specific diseases, whether their overall population screening should be applied, something like you have to check for prostata cancer every few years for males. And the problem with that is that if you have quite a few people who are incorrectly identified as having the problem, then you start doing something invasive, you start causing people psychological issues. So this total screening of the population is not necessarily sometimes a good strategy, just because of this fact. Because of the fact that the prior rate in the population, the base rate is relatively low. And so if you try to find those 2% of the people by trying to screen everyone, that might be a bad way to do it. So you really might want to be more selective maybe about who you screen. All right, another example is Abraham Wald. Abraham Wald was a statistician at Cornell, and he worked with the Navy. And that's one of the problems he worked on. And he never really published it. It was published after things become declassified by other people. And it's actually an example of very careful modeling. So Navy was interested in the problem of reinforcing planes. Reinforcing means you basically take a piece of metal and you apply it, or I don't know, not glue it, but you attach it somehow to an airplane. I'm not sure how exactly they attach it. And the idea is that so that you want to find the most vulnerable part of the airplane, and by reinforcing it with another piece of metal, you just make it more protected, and you want to increase the likelihood of plane coming back after emission, after being damaged. And so they took a data set from one of the missions, and in this data set they had 316 planes that returned back home and 60 planes that did not come back home. And of course, planes that did return back home, you can see what type of damage was caused to them. And 29 had damage to the engine, 36 to the cockpit, and 105 had damage to the fuselage, and 146 had no damage whatsoever. And of course, given this data, you can calculate probability of damage to a specific part of the plane, like here, damage to the fuselage, given that plane returned safely. And for the fuselage case, it's 32%. So out of those planes that returned safely, 32, the largest proportion of them had actual damage to the fuselage. It's just the largest part of the plane, so this is not a surprise that the fuselage is most likely to get damaged. But what you're really interested in is the opposite. You're really interested in probability of returning safely, given that the damage was caused to the fuselage. But you don't really see the airplanes that did not come back home safely. So calculating this one is impossible. And Abraham Wald was able to come out with this imputation procedure that basically allowed him to fill in the missing observations in this table and calculate the probability that he wanted to calculate. So, for example, if you want to calculate probability of returning safely given damage to the fuselage, we have 105 planes that return safely, and then we have 105 plus 8, 105 plus 8, of the airplanes total that has fuselage damage. So more large proportion, 93% of the planes with fuselage damage actually did come back home. So it looks like fuselage is not a big issue. And if you do the same calculations for the engine, you have 29 airplanes did come back home safely, and 29 plus 31 did not. So roughly 50% of the airplanes actually did not come back home safely. So engine is a much more vulnerable part. If you have to reinforce something, you want to reinforce this part of the airplane. Another implication of this conditional probability is what is called personalization. We talked about this new artificial intelligence systems, and they express judgment in a way that reflect their partial knowledge about who you are and what you like. And this partial knowledge relies on the history that artificial intelligence has about you. So, in the case of Google, most of the revenue for Google comes from advertisements, and if they want to maximize their revenues, they need to show you the advertisements that you are to click on, because most of the money comes from advertisements that you click on and not from the just showing you advertisement. And so one of the main problems for Google, problems of making money, is to calculate probability that you click on ad given the past history and your search query. And the past history can be your search history, can be the history of the websites you visited. It can come from cookies or from information that Google stores about you. And of course, the query that you type in the search box also used as a conditional variable. So if you look for something that relates to shoes, you're more likely to see advertisement of a shoe store. And if you look for something related to bikes, you're more likely to see advertisement of a bike store. But anyhow, the idea is that given what Google knows about you, they want to show advertisement that you're most likely to click on. YouTube does the same thing. If you remember old days of YouTube, when you finish watching a clip, you will see this matrix, and it's a 3 by 4 matrix. So you'll have 12 suggestions from YouTube to watch next, and you have to select one of those 12 clips to watch. Nowadays, YouTube doesn't do that. They simply wait for a few seconds. You'll see this spinning wheel for a few seconds, and then they'll start showing in the new clip for you. And the way they do it, they have this predictive model that calculates the probability that you're going to like video, again, given your past interactions with YouTube. And your interactions can be likes that you put for videos, the comments, videos that you watched, videos that you stopped watching, or videos that you watched multiple times. So Google track all your interactions with the platform, and then they try to predict what other videos you're going to like based on those interactions. So again, they're going to calculate this conditional probability of you liking specific video given your past interactions. And then they select a video that you're most likely going to like, and then they just show this video. And they're so confident in their predictive engine, they don't ask you anymore what you really want, they just show it to you. So this is suggestion versus search. What modern internet platforms want to do, they actually want to eliminate search. They um, see search as a burden, and it is actually a burden. So it's a burden for human to search something, and they decide what to select from the search results. So what they want to do, they don't want you to search, they just want to find something that they think you're gonna like and show it to you. So you just have to sit down and do nothing, and the information just get fed to you infinitely. So this suggestion versus search is the result of this modern AI systems. They can do those type of predictions, and there are many business applications to that. And another famous one, of course, is Netflix. Um, Netflix uses this one not only to suggest you movies. So Netflix, of course, has the suggestion also, but Netflix uses to make new content. So all of the movies that Netflix makes or produces based on outcome of their analytics team. They basically analyze again your interactions, things that people like, things they don't like, and then they find the features that people like, and they generate movies that have those features. That's why, for example, Netflix has no pilots. They can save money on that. If you look at the budgets that traditional content providers like networks spend on pilots, that's a significant amount. It's hundreds of millions of dollars every year, and Netflix can avoid those type of expenses just because they're so confident in their predictive models, so that they know what people are going to like even before showing it to people. No need to run pilots.